Welcome, guys, to another episode on our FPGA series. And in this episode, we're going to be talking about floating point numbers. Floating point numbers are fairly important to the math that we do inside machines. And floating point numbers extend the range of multiplications um, or divisions, whatever. It expands the range that we can get to in our math. So let's just look at how these numbers are represented, what are the conventions, etc. So the first thing to mention is that IEEE 754 is a standard to look at. You can Google that, look in Wikipedia, but this is the standard that's been there for decades now. And in this standard, we have definition of single precision, double precision, etc. numbers, and these numbers basically then form the basis for all the math that goes on within our floating point CPUs and the ways that operating systems tackle those. So basically, the mathematical sense for a single precision number can be seen as the following. And in this case, actually, it's just not single precision. Any number could be represented whether it's single or double precision. In mathematical sense, it's the same. It would be minus 1 to the power sine times 2 to the power e, which is some exponent, times 1 dot some fraction, right? Some binary fraction here. So if you can represent any number in this mathematical sense, then we can translate this number into its equivalent machine format. And the way to do that is that you'll just copy this sign bit here. And then the next 8 bits would be this E plus 127 for single precision. This 127 seems to be the bias. And it's just a convention that we would put, this number as plus 127 so that we center around the range, right? And so we have basically the 127 here, e plus 127 as the exponent, and then we drop this one and this dot f. This f is copied as the last 23 bits of the fraction. So that gives us our single precision floating point number. Now let's take an example. If you want to convert pi, so the pi would become 3.1416. The sign is plus 1, which is minus 1 to the power 0, right? Minus 1 to the power 0, and that's why we'll copy the sign as 0. So the representation is minus 1 to the power sign. And then exponent is 2 to the power 1. And if you do 2 to the power 1, which is, if you divide this number by 2, then the remaining number is 1.5708, which nicely fits into our format of 1.f, binary representation. Now, if you do 1.f, the way to write the machine part is that the minus 1 to the power 0, so the sign is 0, exponent was 1, so we write 1 plus bias, which is 1 plus 127, and the last part you just remove the 1 and copy the 0.5708, and if you write that all that is a binary number, you get hexadecimal 40490F F8, and that is the number that would be the machine format of the pi in single precision format. Now, keep in mind that these numbers do not cover the whole range of possible numbers, and floating point numbers will have an overflow and underflow. Overflow when you get too large, and underflow when you get extremely small. You can be beyond the range of what a floating point number can represent. Keep that in mind when you do your math. Now, the next example we'll take is minus infinity. What does minus infinity mean? It's the number over here on this edge here. I'm sorry, on the negative side, it's sitting over here, right? Plus infinity, minus infinity. So if you look at the numbers here, minus infinity can be represented as 2 to the power 128. The sign bit is a 1. I wrote this wrong. I should have said minus 1 to the power 1 instead of saying 1 here. I just copied this sign bit here, but really it should have been minus 1 to the power 1. And 2 to the power 128 is what makes it it's infinity, and the magnitude is 1. So if you do this, the way to write this in the machine format would be the sign bit is 1 because it's a negative number. You will take the 128, add the bias, which is 127, gives you 255 for the 8 bits of exponent. And then you drop this 1 and copy the dot 0. And so it'll be all zeros here. So this number can be represented as hex FF800000, right? So that's your minus infinity, which would be sitting here. Equivalent would be if you drop this negative sign, make this a 0, that would look like 7F800000. That would be a plus infinity sitting over here, right? So that's kind of the single precision, the general representation of numbers. Now let's look at subnormal representation. What happens is subnormal is that you can get really small numbers if you set your exponent to be all zeros. And if you set your exponent, remember that we used to um, do a plus 127 in the case of exponent representation. If this is all zeros, how do you convert that back? I would have done 0 minus 127 here, but the convention for subnormal numbers is slightly different. Remember, this is all just convention, so you just need to remember this. This is not mathematical. So in case the exponent is all zeros, you represent this as 2 to the power minus 126. And remember, in this case, if this is all zeros, the fraction is not represented as 1.f, it is represented as 0.f. Right? So whatever is here, you just copy that here and it becomes 0.f. Right? And the minus 1 to the power sign remains the same. So this is the format of the subnormal numbers. It's slightly different from the normal numbers, and it lets you get down to really, really small numbers, represent them even smaller than the normal range of floating point numbers. Now, this was all about 32-bit numbers. You can follow the exact same logic to get to the 64-bit numbers. And in this case, it would just, all the logic that we have described, you can run the math and you can apply the same laws, same principles, and you'll get to the representations, equivalent representations in a 64-bit math. So hopefully you enjoyed this video. There's more to come on this series because I can talk more about how to apply the real these floating point numbers into doing multiplication and accumulations. Those operations can then help us get to, let's say, representations of neural networks where we would do lots of operations like multiply, accumulate, and then we'll apply some sort of math functions on them, like tanh, um, and or relu, and using those simple multiply accumulate functions, we'll be able to do a machine learning analysis, whether in FPGAs or in Python, and get to some interesting results with just simple math. So math is not beyond this math, and machine learning is not beyond the reach of FPGAs, and it is very exciting that we can get to all that just by doing and being capable of doing some simple math. So that's all for this series, guys. If you liked it, hit the like button or subscribe to my channel, and I'll see you in another video very soon. Until then, take care and thanks a lot. Bye bye.